When people talk about artificial intelligence today, the conversation usually focuses on software, ChatGPT, image generators, AI assistants, and machine learning models dominate the headlines. But there is something most people rarely think about. Behind every AI system is a massive physical machine, an industrial infrastructure made of chips, factories, electricity, and data centers. AI is not just software. It is one of the largest hardware build-outs in modern history. This video begins a series called The AI Supply Chain Explained. In this series, we will follow the physical infrastructure that makes AI possible. From the chips that perform calculations, to the factories that manufacture them, to the power plants that keep the entire systems running. And it all starts with one critical component, the GPU. GPU stands for Graphics Processing Unit. Originally, GPUs were designed to render graphics in video games. Drawing complex images requires performing thousands or even millions of calculations at the same time. Imagine a video game scene. Every single frame requires calculating lighting, shadows, reflections, textures, and geometry for thousands of objects simultaneously. CPUs, on the other hand, the processors found in most computers, are optimized for sequential tasks. They perform a few operations at extremely high speed. GPUs work differently though. Instead of focusing on small number of powerful cores, GPUs contain thousands of small cores designed to perform calculations in parallel. Parallel computing means many calculations happen simultaneously rather than one after another. And this architecture turned out to be perfect for AI. Modern AI models are built using neural networks. Neural networks are essentially massive mathematical structures made of layers of parameters, called weights. When a model is trained, it repeatedly performs operations known as matrix multiplications. And these matrix operations involve enormous amounts of simple arithmetic. Multiplying numbers, adding results, repeating the process billions or trillions of times. This is exactly the kind of workload that GPUs excel at. Instead of performing calculations sequentially, a GPU can perform thousands of them at once. That dramatically accelerates training and inference. Training a large language model without GPUs would take months or years longer. With GPU clusters, on the other hand, the process can be reduced to weeks or months. The company that dominates the AI GPU market today is Nvidia. Originally known for gaming graphics cards and almost going bankrupt many years ago, gradually transformed its technology into a platform for high-performance computing. A key moment in this transformation was the introduction of CUDA. CUDA is Nvidia's software framework that allows developers to write programs specifically optimized for GPUs. Instead of treating GPUs only as graphics devices, CUDA turned them into general-purpose computing engines. Over time, researchers in machine learning began using CUDA to accelerate neural network training. As AI research accelerated in the 2010s, Nvidia's GPUs became the default hardware for training models. And today, Nvidia's data center GPUs, such as the Hopper and Blackwell, upcoming Vera Rubin, power many of the largest AI systems in the world. Major companies including Microsoft, Amazon, Meta, and Google deploy hundreds of billions worth of GPUs inside specialized AI clusters. When we talk about AI computation, we're not talking about a single computer. Modern AI models are trained using clusters of GPUs connected together in large data centers. A single training run for a large language model might involve hundreds of thousands of GPUs operating simultaneously. These machines are connected through extremely high-speed networking technologies that allow them to share data rapidly. The entire system behaves like one giant computer, a supercomputer. Inside these facilities, Rows of server racks contain specialized machines packed with GPUs. The heat generated by these processors is enormous, which is why advanced cooling systems are required. The electricity consumption alone is extraordinary. Some AI clusters consume gigawatts of power, comparable to industrial facilities or small towns even. Although Nvidia currently dominates AI compute, it is not the only company attempting to supply this infrastructure. AMD has introduced competing GPUs targeting data center AI workloads. Meanwhile, several large tech companies are designing their own AI accelerators. Google has developed the Tensor Processing Unit, or TPU, and Amazon is developing its Trainium and Inferentia chips. Despite these efforts, though, Nvidia still maintains a powerful advantage due to its mature software ecosystem, as well as a deep integration into the AI research workflows. And this combination of hardware performance plus the software tooling makes the platform extremely difficult to replace. But raw computation is not the only requirement for AI. Even the fastest GPU cannot function without access to enormous amounts of memory. AI models must constantly read and write massive quantities of data during training and inference. If the memory subsystem cannot deliver data fast enough, then the GPU will just sit idle, waiting for information to come. In other words, compute alone is not sufficient. AI systems require memory that can feed data to thousands and hundreds of thousands of GPUs at extremely high speed. This is where one of the most important technologies in modern AI hardware enters the story: high bandwidth memory. In the next video, we will explore why memory has become one of the biggest bottlenecks in artificial intelligence. Furthermore, we will examine how high bandwidth memory works, why it is extremely difficult to manufacture, and which companies dominate this critical layer of the AI supply chain. Because without memory, even the most powerful GPU cannot do its job.